Now next topic, that is principle of moments or fulcrum or lever. Now an ideal lever, that is the light rod, which one is pivoted at any point along its length. Okay. Now the point where it is pivoted, that is called fulcrum. Now suppose, as shown in the figure, we consider one ideal lever. It is pivoted at point O. So we can say this point O, that is the fulcrum for this particular given lever. Now here, suppose at end A force F1 and at end B force F2 are acting, which are parallel to each other as shown in the figure, as well as perpendicular to the rod. Okay. So here now the distance of force F1 with respect to fulcrum, that is D1, and of force F2, that is distance D2. Now here the lever is a system in mechanical equilibrium. Okay. So here, when system is in mechanical equilibrium, so we can say it is in translational equilibrium as well as in rotational equilibrium. Here at the fulcrum, the reaction R, that is on the rod, or we can say on the lever. So that is the reaction. So we can represent it in upward direction as shown in the figure, and that is in the opposite direction of F1 and F2. So here total three forces are acting. One is F1, second is F2, and third one is R, the reaction. Okay. So for mechanical equilibrium, there should be translational equilibrium as well as rotational equilibrium. Now what is the condition for translational equilibrium? So net force, that should be equal to 0. Suppose here we consider upward force as positive, then downwards are negative. So we can write R minus F1 minus F2, that is the net force, and that is equal to 0. Now for rotational equilibrium, okay, so net torque, that should be equal to 0. So here torque, that is force into perpendicular distance of force from the reference point, means from the fulcrum. Okay. So F1 D1 minus F2 D2, that is equal to 0. Now here conventionally we consider the anti-clockwise moments as positive and clockwise moment as negative, that you have to remember. Clear? So here D1 F1 is taken positive and D2 F2, that is considered as negative. And here this force means reaction, that will not produce the torque, because here torque is calculated with respect to fulcrum. So R itself is at the fulcrum, so it will not produce the torque. Now from equation 2, here we can see when D1 F1 minus D2 F2, that is equal to 0. So we can write D1 F1 equal to D2 F2. Now here D1, that the distance of the force from fulcrum, that is called load arm, and normally this force F1 itself is a load. Okay. And this particular distance D2 of force F2, that is called D2, that is called effort arm, and force F2, that is called effort. Means to lift up this particular load at A, you have to apply the force at B, and that applied force, that is our effort to lift up this particular load at A. Now here when we say D1 F1 equal to D2 F2, so in words we can write D1 that is load arm, F1 is load, D2 is effort arm, and F2 that is effort. Okay, so here the above equation expresses the principle of moment for a lever. This equation itself is called the principle of lever. And here the ratio F1 to F2, that is called mechanical advantage. So from that equation we can write F1 upon F2, that is equal to D2 upon D1. So here we can see this thing, if the effort arm D2 is larger than the load arm, then mechanical advantage that will be greater than 1. When mechanical advantage is greater than 1, it implies that with the help of a small effort, you can lift up large load. Clear to all of you? So this is the principle of lever. Clear?